back. Today we're going to talk about the analytical approach to stability. Okay, so I'll kind of mention a little bit more about what I mean by analytical as we go through the lecture, but here's the basic idea. So we're going to start out by defining what stability actually is. After this, we're going to go ahead and talk about how we can characterize the stability of linear time-varying systems, and then we're going to finish up by talking about the stability of linear time-invariant systems. Okay? So I just want to point out this is the first lecture of our new unit on stability. We're going to talk about this for the next 2 weeks of the class, with today's lecture obviously being included in that. But we finished up our first module on dynamical systems. Now we're kind of ready to go a little bit deeper and start introducing some new concepts. Okay? Okay, fantastic. So that said, let's jump into it. So one, we'll talk about defining stability. Okay, so first what I want to do is I kind of want to do like a little bit of setting the stage for what stability actually is, okay? So it turns out, giving a precise mathematical definition for stability is something that's a little bit harder than it might initially seem, okay? So, just kind of take a moment and see if you could come up with a nice idea in your mind of what it means for a system to be stable, okay? I'll give you a moment to think. All right, so maybe you've taken a moment to think about what might be a stable system. And, if you've taken a class in control before, maybe you said something like, trajectories of the system don't blow up, right? Like if you start small, you'll kind of stay small, right? Something like that. Maybe if you put in small inputs, you get small outputs, and so on and so forth. Basically these ideas, right? So the basic idea is that our system is well behaved in some manner. Okay? So it turns out there's really a lot of different definitions of stability, right? There's like Lyapunov stability, structural stability, Poisson stability, all these different things, okay? So what we're going to talk about today is Lyapunov stability. This is really the most relevant type of stability for the state space picture of control, okay? All right, fantastic. So next week, we're going to talk a little bit more about these other approaches to stability, especially the IO approach. But today, we're going to talk about Lyapunov stability. And we'll take a primarily kind of analytical approach to studying Lyapunov stability of linear systems. What I mean by this is instead of being very algebraic and using Lyapunov equations and all these different things, which we'll do next week, what we're going to do today is we're going to focus on studying stability by proving bounds on the norms of our systems. Okay? All right. Fantastic. So let's kind of give a brief description of the setting for Lyapunov stability. Okay? So the first thing that we're going to do is we're going to say we're actually interested in systems without inputs. Okay? We're going to entirely drop the input term. So we call systems without inputs unforced systems. All right? So we'll say unforced systems. So, for example, in the linear time varying case, we might get, for continuous time, x dot of t equals a of t times x of t, right? So this is the continuous time unforced. And in discrete time, we might have xk plus 1 equals ak xk, right? So this is discrete time unforced. Okay? So, you might be wondering why I'm immediately dropping the input term. So something that we'll kind of see a little bit more next week in the next couple of lectures for this class is that this unforced case actually provides us with a lot of insight into the case where we add inputs back into the system, okay? But generally speaking, with Lyapunov stability, we're not concerned about inputs. We're just purely concerned about the unforced state behavior of the system, all right? Okay. So what I want to do now that I've introduced these kind of unforced systems is I want to introduce some convenient notation. Notation for the state transition map of an unforced system. Okay, so I'll just state this as a definition, because why not? So definition, the unforced state transition map. So I'll say, consider an unforced system. The unforced state transition map is the map defined phi of t, t naught, x naught equals our standard state transition map at t, t naught, x naught with 0 input, okay? So the basic idea is, for the unforced state transition map, we just drop this input term, right? Because we know the input is no longer relevant for an unforced system. Okay? So there's really no need to carry around this extra notation of an input, right? So we just write phi of t, t naught, x naught, because that's all the information we need to know to determine how our system's going to evolve. Okay, fantastic. So with this notation kind of behind us, let's kind of turn back to this problem of stability, all right? So my question next is, how do we define stability, which I'll abbreviate as STB, for unforced systems? Okay, well, my first question is, does it make sense to actually say that a system itself is stable? Well, here's a basic idea, right? It kind of has to do with this question. Our system may have different behavior at different points in its state space. Okay, so with this in mind, does it really make sense to talk about the stability of the system as a whole, at least from the state space perspective? Well, probably not, right? If I have very stable, very predictable behavior in one area, very unstable, unpredictable behavior in another area, then is my system stable or is it not stable, right? So instead of talking about the stability of the system as a whole, because we know stability is maybe an idea that has to do with where you are in the state space, we talk about the stability of individual points, okay? So we instead talk about the stability of points, okay? So special distinguished points in our state space. So let's kind of think about what a candidate point that we might want to analyze the stability of might be. Well, an obvious candidate is a point where if we start at that point, we stay there, okay? So, this kind of seems like a naturally stable behavior, right? If we're coming up with, a particular point and we're declaring that point to be stable, it makes sense that if we start at that point, we should stay at that point, right? If this point is said to be stable. So let's go ahead and formalize this idea. We're going to call this thing an equilibrium point, all right? Okay, so definition, equilibrium point. Okay, fantastic. So what I'm going to do is I'm going to take an unforced system, all right? So I'll say consider an unforced system, right? A system without inputs. Unforced system with state transition map phi, okay? So I'll just assume that this is going to be one of those unforced state transition maps, okay? Whenever I'm dealing with an unforced system, I'll automatically assume I'm using the unforced state transition map, right? Where we drop the input term. Okay, and I'll take the state space to be sigma equals Rn, all right? So I'll declare a point xe in Rn is an equilibrium point of the system if the following is satisfied. So essentially what I want is, if I start at my equilibrium point, I need to stay there, right? And that should hold for all time. So I could write this out in math simply as phi of t1, t naught, x equilibrium equals x equilibrium, right? And this should hold for all times t1 greater than or equal to t naught belonging to my time set t, okay? So all that this is, I'm just saying my equilibrium point needs to be a fixed point of my state transition map, okay? So a fixed point of state transition map. Okay, fantastic. So what properties does this equilibrium point actually have, right? How can we actually characterize these equilibrium points? Well, typically what we do is, at least so far in this course, we kind of define things for these abstract dynamical systems, and then we say, okay, wait a moment, let's kind of make this a little bit more concrete, and let's pull it back to our system representations, right? So in this case, what we're interested in is finding out what equilibrium points of this system are, and what equilibrium points of this system are, okay? Because these are our concrete system representations that we can actually really do analysis on. Okay, let's determine what a characterization of these equilibria are. All right, so I'll state this. Oops, I'm still writing in highlighter. There we are, that's better. So, proposition, characterization of equilibrium points. Okay, so I'm going to state this first for the continuous time linear time varying system, and then for the discrete time. Okay, so first, we'll talk about the continuous time case. So in continuous time, we have that a point xe in Rn is an equilibrium point of the unforced continuous time linear time varying system x dot of t equals a of t x of t if and only if a of t times xe equals 0. And if you want, you could relax this to being held at for all t in R where A is continuous. Okay? This is a nice property of piecewise continuous matrices, right? It turns out, if you change things at a finite number of points, this won't actually end up affecting the equilibrium properties, okay? So just at a finite number of points in time. Okay, so that's the continuous time case, right? We should say a of t times x equals 0. This effectively means that our state has 0 rate of change once we're at the equilibrium point, right? Because our dynamics is x dot equals a of t x of t. Now what about in discrete time? So discrete time. So in continuous time, we had 0 rate of change when we were at our equilibrium point. Now in discrete time, we'll have something a little bit different, right? Because instead of specifying the rate of change, we just specify the next step. So all that we're going to say is, if we start at the equilibrium point, the next step should also be the equilibrium point, right? Okay, so we say a point xe in Rn is an equilibrium point of the unforced discrete time linear time varying system xk plus 1 equals ak xk if and only if x equilibrium equals a at k x equilibrium. And this should hold for all integers k. All right, fantastic. So let me go ahead and just give you a really quick sketch of the proof of this, okay? So what are we going to do first? Well, first let's talk about the continuous time case, and I'll say, suppose xe is an equilibrium point. Okay? So this is an equilibrium point in the sense of this definition up here. Now, what does that mean? Well, that means if I take any epsilon, right, then what I'll have is, any epsilon greater than 0, if I have t plus epsilon t naught x naught minus phi of t naught x naught, where now I'm going to take x naught equals my equilibrium, over epsilon. What's this going to equal to? Well, if xe is an equilibrium point, then this term and this term should both equal xe, right? So this guy equals xe minus xe over epsilon, which is just 0, right? So what this tells us is that our state transition map is always differentiable with ddt of t naught xe equals 0, right? So if we take the limit as epsilon goes to 0 of this quantity above, we find that we just get 0. Okay, so what does this imply? Well, at every t at which a is continuous, we then have a of t times xe equals 0, right? Because the derivative must satisfy x dot equals a of t x of t. Okay, so that's for the first direction of this if and only if. Then for the other direction, essentially the argument is if x dot of t equals 0 for almost all time, Okay, by almost all, I mean, it's equal to 0 everywhere, but on a set of measures 0. Okay, so these are sets that are just kind of ignored by integration. All right, so this is what we have in the piecewise continuous case. If x dot of t equals 0 for almost all time, then if we start at xe, we'll stay there. Okay, so if we start at xe and our rate of change at xe is 0, then we'll stay at xe, right? Okay, so that's kind of the sketch of the proof in the continuous time case. For the discrete time case, there's similar arguments, but instead you want to argue by induction. Okay, so this is a nice exercise to try if you want to give it a go. Okay, fantastic. So that gives us a nice characterization of what these equilibrium points actually are, right? So we see in continuous time, right, it's something that really zeroes out our rate of change, while in discrete time, it's something that needs to be a fixed point of our state equation. Okay, fantastic. So now what we want to do is we want to kind of figure out how we define stability, right, now that we've defined these equilibrium points. So what's next? Well, let's sketch out a basic idea of what it means for an equilibrium point to be stable. Okay, so the idea is that, just speaking at an intuitive level, if I take a point xe, I declare this point to be stable if starting close to the equilibrium point means we will stay close for all t greater than or equal to your start time. Okay, so if I start really close to my equilibrium point, then I shouldn't stray super far away from my equilibrium point, right? So the basic idea that you want to keep in mind is start close, stay close. All right, so if an equilibrium point has this property, we'll kind of say that it's stable. All right, so let's go ahead and formalize this in mathematical language. And it turns out this idea of start close, stay close stability for an equilibrium point is called Lyapunov stability. All right, okay, fantastic. So what I'm going to do next is I'm going to state a formal definition for Lyapunov stability, as well as a couple of other nice variants of Lyapunov stability. Okay, all right. So let me go ahead and write out this definition. All right, so definition, this is Lyapunov / asymptotic stability. All right, so what's our setup for this going to be? Well, what we're going to do is we're going to consider an unforced system, right? This is the kind of setup we've talked about so far. So I'll say consider an unforced system with state transition map phi. So this is going to be an unforced state transition map, right? And state space sigma equals Rn. Okay? So what I'll also say is, in order to determine what we're talking about the stability of, right, we need to consider an equilibrium point. So I'll say this guy has an equilibrium point xe and Rn. Okay. So we say that the point xe is, well, 1, we have Lyapunov stable. All right, so this is often abbreviated as SISL for stable in the sense of Lyapunov. All right, so this is a very fancy sounding way of saying Lyapunov stable, but you could just abbreviate this as SISL if you like. So Lyapunov stable, or sometimes just stable, as it said, is the following. So if for all times t naught, right, for all initial times t naught in my time set, and for all epsilon greater than 0, there exists a delta greater than 0, such that x naught minus x equilibrium less than delta implies phi of t, t naught, x naught minus x equilibrium less than epsilon for all t greater than or equal to t naught. If this property is satisfied, then we say that the equilibrium point is stable in the sense of Lyapunov, or Lyapunov stable. Okay? So the basic idea is I'm giving you a specification of how close I want to remain. Okay? So specification given by epsilon as to how close I want to stay to my equilibrium point. All right, so that's kind of my demand, and then I tell you, well, I can meet this demand by picking a certain delta, okay? So this is start close within a distance delta. All right, so basically we say that our equilibrium point is stable in the sense of Lyapunov, or Lyapunov stable, if given any specification of how close I want to remain to my equilibrium point for all time. I can always find a starting distance such that if I start sufficiently close to my equilibrium, I'll be able to meet that specification. Okay? So a picture that's commonly drawn for this is the following. So let me draw out a set of coordinate axes. Let's say we're working in R2. I'm going to say my equilibrium point's at the origin, like that. Okay? So what I'll first do is I'll say I'm given a specification of a distance I want to remain, and that distance is epsilon. Okay? So how can I guarantee that my system will remain within this ball of radius epsilon? Well, if my system is stable in the sense of Lyapunov, I can find a smaller ball of radius delta, such that if I start within this ball delta, then I'll remain within this larger ball epsilon for all time. Okay? So this is basically what's happening. Given a challenge of any epsilon, I can find a response delta that's able to meet this challenge. Okay? So some quick remarks. This value delta can depend, and usually will depend, on epsilon and your initial time t naught. Okay? So that's kind of due to the order of this definition, right? First, we have this for all t naught in t, then we have this epsilon greater than 0, then delta follows, right? So a kind of consequence of this is that delta can depend on the two things that came before it, all right? So we're not asking that delta be uniform in our initial time, all right? And that's a stronger version of stability called uniform stability. We're just asking that we could find any delta for, any given initial time and any given epsilon. Okay, so that's Lyapunov stability. What else do we have? Well, if we take a kind of close look at this definition, what we'll find is that all we're asking is start close, stay close, right? So the start close was this delta part of the definition, and the stay close was the epsilon part of the definition, right? But this says nothing about convergence to the equilibrium, right? It just kind of says we're going to hang around near this equilibrium for all time. So if we want actual convergence to the equilibrium, we need a stronger stability property, okay? And this is called asymptotic stability. So there's two types of asymptotic stability we'll be interested in. First is local asymptotic stability. So, let me actually write this in blue, like the rest of the definition. So two local asymptotic stability, which is sometimes abbreviated as LAS. Okay, so our equilibrium point XE is locally asymptotically stable if it is 1, stable in the sense of Lyapunov, and for all initial times, t naught and t, there exists some number epsilon naught greater than 0, such that x naught minus xe less than epsilon naught implies that the limit as t goes to infinity of phi of t, t naught, x naught equals xe. Okay? So here there's two parts of the definition. So it's extremely important that we separately ask for stability in the sense of Lyapunov and the limiting condition. Okay? So this limiting condition says that our trajectory converges to the equilibrium point, and then the stable in the sense of Lyapunov condition is exactly what we described up here. Okay? So it's extremely important to note, in general, the limiting condition, right, the asymptotic behavior, does not imply stability in the sense of Lyapunov. Okay? So I'm going to sketch out why this is a little bit further down, but just now know that these are, in general, separate conditions. Okay? These are things that we need to check both of. Separate conditions. Okay, so this is really important. There's two things to check. Okay, so why is this definition local? Well, it's saying that we only get convergence if we start within this sufficiently small radius of our equilibrium point, right? So if this was the local thing, right, where we have stable in the sense of Lyapunov, and if we start sufficiently close to our equilibrium, we get convergence, what would global be? Well, global would just be, let's delete this, start sufficiently close, right? Let's say we converge to our equilibrium point for any initial condition out there, okay? This gives us the definition of global asymptotic stability. So global asymptotic stability, and this is abbreviated as GAS typically, okay? So we say a system is globally asymptotically stable, or an equilibrium is globally asymptotically stable, if XE is stable in the sense of Lyapunov, and for all T0 in T, in all initial conditions, X0 in Rn, we get the limiting behavior, right? We get the limit as t goes to infinity of phi of t, T0, X0 equals XE, okay? So now whether we converge to our equilibrium or don't converge is entirely independent of where we start, all right? So this convergence holds for all initial conditions out there. Okay, so these are our three different modes of stability, which are of primary interest for linear time varying systems. Kind of with this stuff said, what does it mean to be unstable? Well, it turns out there's a really nice and easy definition for unstable, okay? So unstable, we say that the equilibrium point is unstable if it is not Lyapunov stable, okay? Might kind of seem like a little bit of a cop-out, but trust me, this is the formal definition, okay? So if you want to particularly find, what this means, if you want to write it out in mathematical language, it's a kind of nice exercise to try negating the definition of Lyapunov stability, right? Just kind of see what quantifiers you would end up needing to get, okay? So it's a kind of nice exercise to try, but for our purposes, it's fine just to say it's not Lyapunov stable, okay? That's perfectly rigorous. Okay, so let's kind of take stock of where we're at, right? So we've just proposed a couple of formal definitions of stability of an equilibrium point, right? We had Lyapunov stability, or sometimes just called stability, and this is just a formalization of this start close, stay close idea, right? It's kind of like our basic tier 1 level of stability. Then we introduce local asymptotic stability, which is where we have stability in the sense of Lyapunov, plus this convergence condition, which only holds locally, right? And finally, we had global asymptotic stability, which is stable in the sense of Lyapunov, plus global convergence to our equilibrium point, okay? So I had said a couple of minutes ago that, these two conditions, stability in the sense of Lyapunov and convergence, are actually strictly independent of each other in the general case, okay? So I just want to illustrate why this is real quick. So the question is, why are convergence and stability in the sense of Lyapunov independent in general? Okay? So I just want to stress, when I say in general here, I mean for a general nonlinear system, okay? So this definition that I've stated is entirely generic, right? It doesn't appeal to any sense of linearity. This is something that holds for the general case for a dynamical system, okay? So what I'm going to do to kind of sketch out an example where we have a system that converges globally but is not stable in the sense of Lyapunov is I'm going to sketch out a vector field on the circle, okay? So what I'll do is I'll draw a circle like this, and I'll say, let's have an equilibrium point, XE, all the way at the bottom of this circle. And I can figure out a dynamical system by just sketching a vector field on this circle, right? So let's say I have a small vector over there. Now this vector grows and it gets bigger, right? Really big. And it kind of shrinks in again as we reapproach the origin, okay? So basically what's happening is the size of these vectors in the vector field shrink down as they get to XE, which makes XE an equilibrium point, and they grow as you go further out, okay? So what do we have here? Well, we have global convergence, right? Like we follow the vectors on this vector field around, we're guaranteed to converge to XE, right? And that should be kind of clear just from the picture. But do we have stability in the sense of Lyapunov? Let me go ahead and draw a little neighborhood around XE. Let's say that's my epsilon, right? I want to stay in there for all time. Can I find a ball of initial conditions, which is non-zero, that lets me do this? Well, no, right? So this is not stable in the sense of Lyapunov. The basic problem is, if I start even just a little bit away from my equilibrium point, I'm actually going to get carried around the entire circle, right? So I'm going to keep going around this entire circle all the way until I converge back to my equilibrium point, okay? So if I'm just perturbed just by a little bit, I get sent all the way around this circle until I converge back to my equilibrium. So what this means is that we'll leave any neighborhood around xe, okay? And this property where, if I start a little bit away from xe, I'll leave any neighborhood containing xe, this property violates the definition of stability in the sense of Lyapunov, okay? So this example, you have global convergence, but what you don't have is Lyapunov stability, okay? So it's important to keep in mind this is for the general nonlinear case, all right? For the linear case, things end up being considerably simpler, and we'll kind of see this as we go along, all right? Okay, so this pretty much concludes our first point, right, where we want to come up with nice, precise definitions of stability in state space. Now we're ready to actually try to characterize these definitions in the linear time varying case, all right? This brings us to our second point. So this is stability of linear time varying systems. Okay, fantastic. So remember, our unforced linear time varying systems are the systems of the form x dot of t equals a of tx of t, and x k plus 1 equals a of k x of k. Okay? So what we want to do now is we want to characterize the stability of the different equilibrium points of these systems. All right? So let me first ask you a question. Given those basic characterizations we came up for earlier, what are some obvious equilibrium points for these systems? So what are some obvious equilibrium points, right? Well, there's one that really sticks out, and that is xe equals 0, right? Based on our characterization above, 0 is always going to be an equilibrium point of both of these systems, okay? So this is kind of the obvious choice, and it turns out xe equals 0 is the most important equilibrium point for linear systems. Okay? And the reason for this is that, as we'll see a little bit later, is the only equilibrium point of a linear system that exhibits asymptotic behavior. Okay, so we'll later prove, in a few, maybe 10 or 15 minutes, that if we have an equilibrium point of a linear system that is asymptotically stable, then that's guaranteed to be the 0 equilibrium point, right? It cannot be anything else. Okay, so the 0 equilibrium point is a pretty fundamentally important equilibrium point, right? It's kind of the canonical choice of equilibrium for linear systems. So what we're going to do now is we're going to try to come up with really sharp characterizations of the 0 equilibrium point, okay? How are we going to do this? So, next question, how to characterize stability of xe equals 0?